Então, boa tarde. Agradecemos a presença de todos aí que estão acompanhando o seminário pelo Google Meet e também pelo YouTube, né? Meu nome é Reinaldo e junto com a Maria, a Victoria, que está dando tchau aí, nós estamos organizando, junto com o departamento, né, o ciclo de seminários desse semestre. E nós temos o prazer aí de iniciar o ciclo com o convidado, o Dr. Juan Carlos Rodríguez-Ramírez. E, primeiramente, obrigado, Juan, por aceitar participar, por aceitar esse convite. E eu vou pedir a todos, por favor, que desliguem os microfones e as câmeras durante a apresentação, né? E vamos usar o chat aqui do Meet para indicar quem quiser fazer uma pergunta, né? Já pode ir anotando aí, escrevendo no chat quem quer fazer uma pergunta para o Juan depois da apresentação, que a gente segue essa ordem aí que for colocada. Então, good afternoon. Thanks everyone for the presence in the seminar who are following via Google Meet or YouTube. My name is Reinaldo, and with Maria Victoria, we are together with the astronomy department organizing the seminars cycle of this semester. So it's our pleasure to open this cycle with the invited speaker, Dr. Juan Carlos Rodríguez-Ramírez. Thanks, Juan, for accepting this invitation. So please, everyone, turn off the cameras and the microphones during the presentation and use the chat to indicate that you have a question for Juan at the end of the presentation. So Juan has a degree in physics by the Universidade Nacional Autônoma do México, a UNAM, a master and PhD in astrophysics, also by UNAM. And since 2017, he works as a postdoc researcher at IAG, working with the plasma and high energy group. He has research experience in the star formation field, and now his main interest is in high energy phenomena. Today, he will talk about the emission signatures from massive black hole binary systems. So, please, Juan, thanks again, and you can start.
So I have to share my...
Yes.
All right, so let me know if you can see my screen.
Yes.
Can you see? Okay. So I am assuming that also the volume and the sound and everything is okay. All right. So thank you very much for the invitation and for the presentation. And then, well, I would like to share with you these very recent results that we obtained in collaboration with Pankaj Kushwaha, who I guess is present here in this seminar, Professor Elizabeth de Goya Dalpino, who is our supervisor. Pankaj was a former postdoc in IAG, in the high energy plasma group, and also together with Reynaldo Santos Lima, who is the presenter, the organizer of the seminar. So we were doing a theoretical model to interpret the major flare of the source OJ287, which apparently is claimed to host a supermassive black hole binary. The thing is that so far it's not possible to trace this kind of systems through gravitational wave detection, but there are some techniques with electromagnetic radiation that can be used to trace this kind of objects. So in this talk, I am going to first give some elements as an introduction in order to, let's say, understand each one of the components that we are using to model this flare. And then I will describe very briefly the features presented by this blazar. Then I will be describing the thermal plus hadronic emission model that we developed. And finally, I will list some conclusion. So probably you are more familiar with stellar mass binary black holes. Probably you know that in 2016, the collaboration of LIGO and Virgo reported the detection of gravitational waves. which are expected in the Hertz 100 Hertz regime. And well, this kind of sensitivity of these instruments is for black holes of what is, they are called solar mass black holes, around less than 100 solar masses. In the case of supermassive black holes, which are black holes with solar masses above 10 to the power of 5 solar masses, it is not possible to detect them through gravitational waves directly because there is no current instrument capable to do this. However, it could be possible to trace them through electromagnetic signatures. So far, is not they have not been detected. They have not been resolved at parsec or sub-parsec scales, where they are expected to emit gravitational waves, and their orbits are expected to decay by this. So what you are seeing in the right-hand side in this figure is a simulation yet of a collision of two galaxies, which is thought to be the most likely mechanism to lead to these pairs of supermassive black holes. But motivation to look for this kind of system could be that, well, if these pairs are merging, they could release the most powerful sources of gravitational waves in the universe. So this would be places of the highest, with the strongest gravitational fields. This is, as I previously mentioned, expected as the current standard model for cosmological model, the lambda cold dark matter model, indicates that formation of galaxies occurs hierarchically. Then also an interesting question would be how supermassive black holes of masses above 10 to the power of 5 are formed. For instance, it has been spotted black holes with a black hole with 10 to the power of 8 solar masses at a redshift of 7, equivalently to the age of what we think is the age of the universe when it was 0.7 gigayears. The thing is that the question that arises is how this very massive black hole grow. How is this black hole accreting through hyper or super Eddington rates, or what is the process that for this kind of black holes? This is an interesting question, and also because gravitational waves travels also practically undisturbed, this would provide information of the first galaxies in the universe. Another interesting question could be the final parsec problem. The final parsec problem is an issue where two black holes in a fusion of two galaxies are expected to approach each other because they lose kinetic energy through dynamical friction. This is because they deflect the mass and stars in the surrounding, and then they release the kinetic energy to them, and then this produces that their distance shrinks. However, when they are approximately at parsec scale of distance, there is no enough material, according to estimations, to produce this release of kinetic energy through dynamical friction, and then they could last too much time in order to enter the regime for gravitational wave decay. So they could even stall the age of the universe 10 to the power of 9 years, and therefore we will never see pairs of black holes coalescing. However, there are some other processes suggested in previous works that solve this problem, but still they are theoretical, and well, the only way to investigate if it is possible or not to have pairs of SMBH merging and releasing gravitational wave is through direct detection of these signals. But so far, since there is no current instruments There are some projects that aim to build instruments through different methodologies. I am not going to talk about them, but they deserve, I think, another seminar. But so far, it's possible to investigate which astrophysical objects contain pairs of close supermassive black hole binaries through electromagnetic signatures. For instance, AGNs typically emit line emission. If this line emission is displayed as double-peaked, this indicates that due to the Doppler shift, there's motion of the source of this line emission, and this could indicate the presence of a supermassive black hole pair. The idea is that, well, whereas it is not well understood what the broadline region is, but a very idealized model could be built if it is considered that each AGN orbiting each other contained a cloud, or let's say a set of clouds attached to each other, and then their emission will be affected by the motion through blue and red shift. This is what produced the double line emission. Also, well, in other scales, but not well understood yet either, narrow emission lines also can be studied in this double-peaked form. The problem with these interpretations, or I don't want to say the problem, but the challenge of these interpretations is that this is not the only explanation that could explain these morphologies. Other processes like two-side outflows, jets, or rotating structures could also produce these double-peaked morphologies. Another way to trace the presence of supermassive black hole binaries is perhaps through the semi-periodic light curves that they emit. For instance, in the optical, there's two objects that are remarkably have been fitted with the sinusoidal signals. For instance, this blazar PG 1302-102 displays an about 5 years periodicity. This blazar has not currently a solid interpretation or a solid model that can explain this periodicity, but the periodicity is measured. And the other case is the blazar object 287, which is the main focus of this talk, which displays also optical periodicity of around 12 years. And it has been studied, or it has been recorded since over 1 century. This blazar has been a bit more studied, and there are several mechanisms or several processes and theoretical models that try to explain this variability. This blazar is located at redshift 0.3, and the most peculiar figure in the light curves is that they present double-peaked variability in time, and with separation with about 1 year, which probably suggests that this could correspond to collision in a double collision in an orbit of a secondary black hole. That would be like the straightforward, let's say, a clue. Here you are seeing an image of this object in radio and in X-rays. And well, this is what we think it is. It is a blazar. Probably you are very familiar with these objects. A blazar is AGN, which is accreting material, and is also launching powerful outflows and very collimated. The characteristic of these outflows is that they are directly toward us. So their emission obviously will inherit this, the particularities of this collimated outflow directed toward us. And well, as I mentioned, particularly in this source, the most peculiar feature is that there are two peaked morphology in the light curve. Alternative models to the hypothesis of the binary pair would be the one presented by Britzen, which Britzen et al. Explain the light curve of this source with precession of jet. However, they do not rule out the presence of a supermassive black hole pair, because this precession could be also induced by the motion of the secondary black hole. Probably the most, let's say, accurate model for this variability would be the model proposed by Leto and Balton in 1996, in which the secondary black hole plunges the accretion disk of the biggest one, and this produces the flares observed. They can match the light curve with this model. The difference with other models is that this plunging black hole model can explain the fast, sharp of the flare, can explain the timing of the flares, and also, this is probably the most important feature, that this explains the low polarization degree observed in the emission, which make them attributed to the thermal emission and not synchrotron. Well, but how these flares are produced by this binary system, how this thermal emission is produced by these collisions? I will briefly introduce the model, because this will be needed to understand our contribution to this line. And well, the model is basically the following. Consider in this map that at the center, at the origin, you have the primary black hole, and you have another black hole with approximately 2 orders of magnitude less mass, which is orbiting, and which orbit could be modeled with post-Newtonian approach. So every time that the black hole crosses the x-axis, where the x-axis is supposed to be the thin accretion disk of this blazar, the flare will be triggered. The thing is that the flare is not triggered exactly at the same moment where the orbit crosses the accretion disk, but there is a delay in time, as is pointed by the arrows. This delay in the time depends on the model that is adopted to explain the emission. To understand how this emission is produced, consider that this volume enclosed by the distance of an impact. The distance of an impact is r imp here in this cylinder. And then when the secondary black hole threads the thin disk of the primary one, it will start accreting in a Bondi-Hoyle-Lytton fashion, where the resultant velocity is the velocity of the orbit of the black hole and the velocity of the accreting disk, the accreting material. In the right-hand side, you see cartoon in the frame of the traveling black hole. And well, to understand how the energy is released, you can consider that the Bondi-Hoyle-Lytton radius is a cylindrical radius below which all material impinging into the black hole will be accreted. But above or beyond this radius, there's material that is deflected by the gravity of the black hole, is compressed by the shock produced, but it has enough kinetic energy to not fall into the black hole. So we consider that this material is the one that produced the flares. And we can easily calculate or estimate the energy of this material just with the conservation of kinetic energy in the upstream direction and mass. And then assuming that this is split into outflows, we can see that each outflow could be proportional to the square of the velocity of the impact, the gas density proportional to the gas density of the disk at the distance of the impact, and is sensitive to the bonded Hoyle literature radius of the impact. This effect has been simulated in 1998 by Ivanov. In this case, I am displaying here a result of a hydrodynamic simulation of the collision of a black hole onto an accretion disk. I repeat, this is purely hydrodynamic simulation, but the result is that after the secondary black hole threads the accretion disk, first the accretion disk is bent, is warped, and also two outflows emerge from this event. To simplify matters, Lethan-Baltonen in 1986 approximate these outflows and its emission as spherically growing volumes. The flare then is produced when this spherical volume is optically thin to Thomson scattering and to absorption. Therefore, the most important quantity here is the effective optical depth. The effective optical depth could be understood in a diffusion approximation as, let's say, initially, the outflow is optically thin in a very thin shell, but as the outflow grows, the gas density, the temperature, and also the volume makes that this external shell goes into the center, and therefore the full sphere can be considered as optically thin at certain frequencies. When this occurs, well, we can claim that the optical outburst is produced. And then it is possible to calculate the spectral energy distribution and compare with the quiescent state. In this slide, I'm showing a comparison among the quiescent state versus the flare state corresponding to the 2005 outburst in the paper of Balton in 2012. And so this probably is the case if the requirements that the low polarization degree and the shape of the spectrum fits with this thermal explanation. Well, everything was explained in terms of thermal emission until very recently. In 2018, Pankaj Kushwaha, our collaborator and former postdoc of the IAG, analyzed the multi-wavelength light curve of the 2015 major flare. There was not only optical flaring, but it was also detected in X-rays and gamma rays simultaneously. Therefore, if this is produced by an impact of a black hole plunging into the accretion disk of a bigger one, because this is simultaneous, this could be also the source of the multi-wavelength, or, well, the question here is, what is producing the high energy counterpart of this light curve? Is it possible to account with the same model? Another interesting fact that occurs in 2017 was that at the energy bands of TVs, this is TV's electron volts is around or beyond 10 to the power of 26 hertz in frequency. The Veritas detectors also spotted emission from this source, OJ287. Well, this emission was not simultaneous with the claimed impact or the predicted impact, but it's still interesting if these two events are related. In order to make a comparison of what is going on at the moment or after the impact, I am presenting two spectral energy distributions from a paper of Pankaj 2020, where, well, typically flaring in this source present enhance in the flux in X-rays and gamma rays, but the spectral index do not vary that much. And also, well, in the flare moderated and quiescent state in the left-hand side of this in this plot, the optical emission was not varying too much. This is very different if it is compared with variations in the emission corresponding to the predicted impact or black hole impact. In the right-hand side, you can see in magenta the change in the spectral index in comparison with what is considered the quiescent state in red symbols. And well, the particularities, as I previously mentioned, is the low polarization degree initially, and also the hardening in gamma rays. So if this is coincident with the so-claimed black hole impact, what we are trying to investigate if this can be also produce the high energy counterpart. And if it is not possible, therefore the mechanism for the simultaneous high energy counterpart would be other, but well, probably if this could be a problem for the hypothesis of the black hole binary. But with this, what was the following? Sorry. Oh. We consider the persistent model of the outflow that I previously described, which explained very well the optical flares. But we consider the interaction of this outflow that with the AGN wind. As the outflow grows and impinges with the AGN wind, there is a shock that accelerates particles. And well, under this hypothesis, we started to derive what would be the high energy emission. The cartoon is the following. For the shock to form, it is necessary the impact to occur far beyond the region of the corona. Here in the upper panel, there is a cartoon, a very idealized situation where you have an accretion disk and you have an AGN corona, which typically has temperatures of 10 to the power of 10 kelvins, and the speed of sound is very high. Therefore, creation of shock waves, acceleration of particles there could be difficult. However, as it is the case of the 2015 flare, according to previous models, the impact occurred at approximately 100 gravitational radii of the primary black hole. And therefore, at these distances, models for AGN winds can attain velocities of around 0.1, 0.2, a significant fraction of the speed of light. Assuming this, the interaction of these two outflows forms a shock wave. The conditions for these shock waves can be obtained by just to imposing that the magnetosonic Mach number must be much more than 1. This is, I think, very familiar to all of you. Assuming a very simple model, we can constrain or at least set lower and upper limits for the properties of the AGN wind in order for this shock to be supersonic and accelerate particles. And then the most important point here is if this energy impinging in the outflow, in the impact outflow, could be enough to power the observed gamma ray emission. To calculate this energy, we consider that 1/10 of the kinetic energy impinging on the outflow bubble could be converted into cosmic rays. This is, let's say, standard in particle acceleration models. So we can assume this with as a conservative assumption. And then we very easily calculate the total energy with at the end is in terms of the gas density of the AGN. the initial radius of the growing bubble, the initial velocity of the bubble, and the velocity of the AGN. With diffuse shock acceleration, particles then would need to travel or to diffuse into the body of the bubble outflow. Why? Because the bubble outflow is very dense, and this is the main target for, let's say, high energy emission, like proton-proton interactions. Proton-proton interactions generate neutral pions, charged pions, and charged pions generate electron-positron pairs, and also neutrinos can be generated. But here we are more interested in the neutral pions generating gamma rays and the charged pions generating electron-positron pairs, because the emission of electron-positron pairs could be detected or could be compared with the observations. Here, this is something what I was previously mentioning, that the ideal place for particle acceleration is the swept-up shell of shocked material. In the left-hand side, you have a plot of the characteristic time of acceleration and losses of cosmic ray protons as a function of their energy. Then the main cooling mechanism that are obstaculating the acceleration of this proton is the diffusion, the losses due to diffusion. And we see that, this dotted gray line is the time where, or the elapsed time where the bubble grows from R0 to the moment of the flare. Therefore, typically in this process, with our estimations, we obtain that particles, cosmic ray protons, can be accelerated up to around 10 to the power of 11 electron volts, which are more than enough to produce the gamma rays observed in the spectrum. Here in the right-hand side, you see a plot of the characteristic time versus the energy of particles, but within the outflow bubble. Within the outflow bubble, the electron-positron pairs cools very fast in comparison with the lifetime of this outflow bubble. And also, if you compare the curve corresponding to the proton-proton interaction, which is the orange one here, compared with the orange one on the left, you see that proton-proton interactions are much more efficient within the outflow bubble than in the swept-up shell of shocked material. Therefore, the main target for this very high energy emission is the outflow itself. And here you have a multi-wavelength spectral energy distribution of the flare event that I was talking about, the 2015 flare, but with X-rays and gamma rays components. If you are not very familiar with this kind of diagrams, in the y-axis you have flux of energy per unit as area per unit second, and as a function of the frequency of the radiation. So this tells you specifically in each frequency what is the energy released in photons from the source. And in the black dashed curve, you have a model for the quiescent state, which is aimed to model the magenta data. The magenta data is what we consider the quiescent state of the source. And then we compare with the data in green, which is the flare state. And then, we account for the high energy processes that I previously described in order to find the conditions and the properties of both the AGN wind and also the outflow bubble that allows to explain this emission. Here in the orange curve, you see the component due to the thermal bremsstrahlung produced by the outflow bubble. In the red solid curve, you see the emission due to gamma rays directly from pi on the K. The annihilation of gamma rays produced by the soft radiation of the thermal Bremse stratum emission is noticeable here in a cutoff of the spectrum. And the secondary electron-positor pairs produce synchrotron radiation, which is this dotted curve here, and also inverse Compton scattered. Inverse Compton radiation, which are electrons scattered from the thermal radiation of the outburst. In this case, we consider that the thermal photon field is the main target for inverse Compton scattering because, well, the synchrotron emission produced by these leptons is not, it is around 2 orders of magnitude lower than the thermal radiation. So the dominant target for inverse Compton scattering is the thermal radiation. And also another feature here is that the synchrotron emission of the secondary electron-positron pairs, as I mentioned, is 2 orders of magnitude lower than the thermal radiation. And therefore, if this radiation would be polarized, they do not contribute to the overall optical flare in this nature. Therefore, this is consistent with the condition imposed by the observation that this emission should be with low polarization degree. This is not necessarily the case because even synchrotron radiation could be depolarized in turbulence in the AGN wind, but well, this is another story, and probably this is beyond the study that we are discussing here. And well, we obtain different models that requires a magnetic field of around 5 Gauss in the acceleration region. This could be produced by amplification of magnetic field. There are several mechanisms. We are not discussing exactly which one. We are only finding what would be the magnetic field that fulfill the SED requirements. And also the population originating the high energy counterpart is consistent with a power law index of 2.2. This is, let's say, in agreement with the standards. And the maximum energies of these cosmic ray protons are around 0.5 TeV, tera electron volts. This is 10 to the power of 12 electron volts. Or, this is 1 TeV. Well, the energetic or the luminosity power of the AGN required to produce this high energy emission is of the order of half of the accretion power of the primary black hole. So I am here now with my conclusions. Just as a summary, currently it is not possible to trace pairs of supermassive black hole through their gravitational waves, but there are techniques or there are some methods that can allow us to trace them through electromagnetic signals. What we did was to interpret the multi-wavelength spectral energy distribution of object 287 in terms of the presence of a supermassive black hole binary. So for this, we require emission of cosmic ray protons and the presence of an AGN wind. Future simultaneous broadband outburst can be used to constrain the nature of these pairs of black holes coalescing each other, or rule out this hypothesis if some characteristics of this simultaneous broadband is not able to be explained by this scenario. And well, thank you very much for your attention, and this is all that I wanted to share with you.
Hi. Thank you, Juan.
You're awake.
Very clear presentation. And now we will open space for the questions. I think the first one, Katarina has a question. Please, Katarina, go ahead.
Hi, Juan. How are you?
Katarina, how is it going?
Fine, thanks. Thank you for the presentation. Really liked it. I had a few doubts on the models. I think it's more on the part of the hydrodynamic models, because it seems like there is the primary black hole, then the accretion disk of this primary black hole, and then the secondary black hole would not have an accretion disk. Is that it?
Okay. Well, yeah, you are very right. Actually, the accretion disk is formed, I would think, if there is enough material to accrete, right? Well, if the secondary black hole is traveling, let's say, far away from the disk where the gas density probably is very low, probably the accretion disk is very faint. Your question is very interesting, because when the secondary black hole here is threading the very dense zone, there is a lot of material accreting, and a disk could be formed here. Well, the thing is that we are here at the scales of the von de Hoyle-Littleton radius is approximately, if the velocity of the impact is around 0.1 c, the speed of light. This radius is around, if you compare this with the Schwarzschild radius, this would be like 100 lower. Sorry, 100 bigger than the Schwarzschild radius. Therefore, if there is an accretion disk, it could be in smaller scales, but certainly this will contribute with radiation. So, well, the thing is that it's not considering this model, but if that would be the case, it would be a very small in comparison with the scales that we are discussing here. I don't know if this is what you were asking.
And can I ask something else?
Yeah.
In this interaction where the secondary black hole passes through the accretion disk, the outflows, the energetic output would come from the disk and not from the black hole, right? Like the black hole wouldn't miss mass until it collapses with the primary, or not?
Well, it comes from, the energetics comes from both. As you see in this diagram, if you go into the frame of the traveling black hole at the moment of the impact, this VR velocity is the resulting velocity of one, the rotating material around the primary black hole, and two, the velocity of orbit of the threading black hole. So this composite velocity would end up with the resulting velocity VR. And well, this is what is taken into account for the energetics. So are both. Actually, if the rotating velocity, the Keplerian velocity of the disk could be negligible in comparison with the orbit of the black hole, we would have here only the velocity of the traveling black hole. I don't know if this answered your question.
Yes, thank you very much.
No, you're welcome.
Now we have a question from Maria Victoria. Please go ahead, Maria.
Hi, Maria.
Hi, can you hear me?
Yeah.
Okay, very interesting. Your talk is very interesting.
Thank you.
Also, the phenomena is very interesting. I have a question regarding to your model for explaining the flare.
Okay.
So, as far as I understand, the particles, the protons, are accelerated in the bow shock that is producing the impact, right?
No. Okay. Actually, this was like the first possibility that we considered, but this was not the case. You mean to say this bow shock here, just in this figure in
No. The protons that are producing the gamma rays from the flare, where are they accelerated?
Okay, they are accelerated after this impact occurs, and then the outflows are released above and below the accretion disk. We consider only the one in the side of the observer, and probably here in this cartoon. Oh, where is this? Where is it? Here.
Yes.
Okay. Then I don't know if this is understandable, that the impact occurs here, and then you have a release of two outflows. When this outflow in the direction the observer starts to grow and interact with AGN wind, then you have here in the low panel, you have a bow shock or something that we think or we imagine is a bow shock. The thing is that this is a very idealized situation. Actually, the outflows, they would be very far to be spherical. But, well, following this very idealized model, the cosmic rays are accelerating in region, let's say, between region 1 and 2. What we need is that these cosmic rays migrate into the outflow, because the outflow, the body of the outflow, this spherical volume, is the main target for proton-proton interactions.
And so, of this protons population, how much of these protons do you need?
Oh, okay. You need the protons in order to match
to interact with this.
Well, you need the protons necessary to match the observations, but the energetics
because you would have propagation effects.
Oh yeah. Well, the thing is that we assume that basically the energy impinging this bow shock, we take 1/10 of this energy and we convert them into cosmic ray protons here with this equation. And well, this J is the population that you are talking about. This is the power law with a exponential cutoff. Well, this is what normalizes the energy, and this EW is the cinetic energy impinging during the time of since the bubble emerged until the flare. So this is all the energy that was, let's say, all the energy that was impinging the outflow. And then you can derive this in terms of the basic properties of the outflows and the AGN wind. So this is how we set the energetics. I don't know if this answers your question.
Yes, yes.
And what do you think? Is this appropriate?
Considering the 10%, yes, of course.
Okay. So this is conservative, right?
Yeah, I think yes, because I suppose the shock is very fast. You mentioned that these winds are really fast. So
this could be measured with if the shock is is hypersonic or supersonic with respect to the magnetosonic speed.
Juan, I have a question myself. So this scenario to explain these flares of the precessing jet, it's not ruled out. Not yet.
Not yet. Well, at least we are not ruling out this with this model. Actually, our result would favor this binary system if there exists an AGN wind and if well, the bubble behaves as we are describing here. The thing is that I don't know if this is a good question. If there is no, can I rephrase your question? Imagine if the black hole binary holds, the black hole binary hypothesis holds, but it is not possible to reproduce the broadband emission that is only responsible for the optical flares that it has been came before. Then where and how is produced the X-rays and gamma rays if they are simultaneous with the optical flare, but not produced in the outflow bubble produced by the impact of the secondary black hole? If it is not possible to be explained with this model, probably the origin is other, but I found it very difficult. Or what do you think?
Maybe you have some idea, maybe someone who is participating here also has some opinion. Is there a kind of, from the observational point of view, to rule out one of the scenarios, maybe with future observations?
Maybe with future observations, right? With future observations, and also because formerly there was not gamma rays facilities.
Gamma rays
data, but I think in the future there would be possibility to clarify this.
Perfect. No, next is Pankaj. Maybe he has also some comments.
Yeah, okay. Can you hear me?
Yeah, Pankaj.
Okay. So this is comment about Ronaldo, about whether if we can rule out the two scenario. I think it was like a jet emission, or whether this is the binary black hole impact, right?
Yes.
So okay, so there is a specific observation in, the flare that Juan is discussing. The in the jet, the emission in optical is purely synchrotron. Okay. So if you take, and synchrotron is broadband, and what we found is a feature in the infrared, near infrared, and optical, which is too sharp. So if you try to, let's say, conclude, extract spectrum, what is the slope of that mismatch between the optical and infrared observation, you'll find that it is like 2.75 or 3, which is like close to a black body. Now, synchrotron is broadband, so you cannot explain that sharp feature, unless, of course, your density is so high that the synchrotron self-absorption occur in optical band, which is less likely. So if you just go purely by light curve, the two are more or less similar. The only difference is polarization, but again, the confusion remains, because even in the jet scenario, you could have a flare, but very less polarization when turbulence is present. But this was much more restricted when you look at the spectrum. So you see that there is a sharp cutoff, and sharp cutoff is not a feature of at least the optically thin synchrotron. So it provides more, it's more likely favor the model, the binary disk impact model. There is another thing. The other thing is that if it is purely due to jet, and if there is nothing changes, you should see simultaneous flaring in all, because jet is precessing. So the flare that you should see from radio to gamma ray should be at the same time, but in radio you often don't see at the same time.
All right.
So this more or less favors the other one, but still it's open. But the other, one of the good part of this model is that it can surely predict. The best part of this is the predictability. You can predict that this next flare will be between this and this time. And so far, it has been quite consistent. It has not been possible in the jet precision model yet.
Perfect.
But what about, okay. Can I ask you a question?
Yeah.
What would be the explanation if the thermal flare is explained by the impact scenario, but the simultaneous high energy components are not attributed to the same event?
No, so the problem is, I see it as other way around. Like, the problem is that this model of that this system is actually a binary black hole system, where the one of the black hole impinge on the primary black hole disk, and this leads to the production of optical flare. This is basically driven from the observational data, and the only observational data that we have mostly so far, like the century old, is optical. Okay, so actually nobody bothers about the X-ray and gamma ray, because neither we had that sensitive instrument at those time. Like when it was discovered, this tendency was noted in the 71 and 83, and then the paper published was in 88, and then they predicted that it should be in 94. If this model is true, we should see it. Okay, so they more or less focused on the optical part, and there is many things you can ask why. So the one good part of the optical is like the source is very bright, so you can it can be detected within a few minutes. But in the X-ray and gamma ray, okay, at least in gamma ray, it is not possible that it may be detected even in a day. So it is not that precise when you see it with respect to optical. So these people have not focused on the X-ray and gamma ray so far.
All right.
So that's what I will say. This is purely biased, I think, because of the observation that we see.
Perfect. Now let's go to the last two questions.
Okay, so now can I ask my question?
Sure.
Yeah.
Okay, so the thing is, like, see, this model, let's say, predict that the impact actually happened in the black hole frame, somewhere around 2013, and what we see, the flare is delayed in 2015, as you saw in one of the plot where this precision model was shown. Okay.
This one.
Yeah, this one. So the impact happened at, let's say, somewhere it says, the arrow marked the position when the secondary black hole actually emits when the emission was observed.
Exactly.
Okay. Exactly. So the thing is like, we are, so what I don't understand is there is any study, if you are aware, whether the disk impact happens at hundreds of Schwarzschild radii, some 50 or more than that, and that the wind will be launched immediately, or it will be after some time?
No, there is another delay, you certainly said. So are you talking about that after, let's say, the secondary black hole meets the accretion disk, how much time would it last to emerge from the disk? Is this what you are?
No. So there is, no. So the thing is like, we are explaining that there is this blob emerges, and then there is a Aegean wind, and the interaction cause this particle acceleration and the emission. Okay, high energy emission, right?
Right.
So the thing is that the blob is emerging, and there is always a Aegean wind. Let's say if I assume that there is always a Aegean wind, so the blob is already emerging, and so it should start emitting at those point of time, isn't it?
Well, it depends, because as you know, the blob should be optically thin to emit in thermal, and in the high energy part, the particles need sometimes also to accelerate. So to attain some energy is necessary to explain, let's say, some energy band. For instance, here in this plot, where is this? Here, you also see in the left-hand side panel, you see the acceleration time required in comparison with the lifetime of the blob at the moment of the thermal flare. The thing is that probably you are right. You are suggesting that probably high energy emission comes before the thermal flare. And the thing is, we are only reproducing the SED that is simultaneously. That's why we take as a reference the moment of the thermal flare and how was the SED at that moment. But according to this, the energy required to energize the gamma rays that we are seeing there, they are ready before the thermal flare. And because the shell is optically thin, probably they emit before. Well, this is something that we have not checked, but probably this is this what you are, is this in the line of your question?
Yes, so the two confusing thing that I have is this. So we see that the Aegean wind is interacting with this blob, but then the flare at the moment when the blob is optically thin. Okay, so which also said that the density is very, very less compared to what it was earlier, isn't it?
Well, for the high energy part, they could only interact like in the external surface of the blob. And then
yes, so exactly that's what my question was. Like then the at least because the blob is already there for 2-3 years until it turns optically thin, so that we see the flare in optical. But since the wind is there and the blob is also moving, in the gamma ray we should keep seeing this signature, should not we?
Yeah. Well, in the gamma rays, and probably also in the X-rays, because we are attributing the X-rays to the secondary leptons, they should be there. The thing is that I don't know if they are faint or they are, let's say, strong enough to be detectable. Why? Because remember that we are also normalizing the total energy of this population with the energy of the wind, probably at times smaller than the time of the outflow. There is not enough energy in cosmic rays. Probably they attain high energies, but the total population is not, let's say, enough to produce detectable emission. So, well, this is something that we can do, the time evolution of this this scenario.
Okay.
Okay.
Okay. Let's go to the last question. I don't know if William is still in the. Yes. So the quick last question.
Really nice talk, Juan.
Hi, William.
That's very interesting. So my question is, I have two questions. One is about the predictions. If you have some prediction, or if you are able, guys, able to predict some phenomena with your model that that could be observed by or to make some measure in the near future with your model.
Mm-hmm. Well, the first thing is that what we are predicting is the past SED. So what happened before. In the future, well, this is very interesting because in the future, if the scenario is right, you see the orbit is predicted to impinge in 2022. The next let's say the next collision of the secondary black hole with the disk. Therefore, we will have at that time another flare. The thing is that as the impact occurs closer to the corona or closer to the primary black hole, it is kind of difficult to accelerate particles because the temperature starts to increase if there is the so-called corona, if the existence of this corona is actually the case. So, well, we can repeat the same exercise for the next events that are predicted by the model, if this binary model is true.
Okay, and another quickly question is about the feedback. So your model, can I for example take your model and take and calculate some numbers about for example, the increase in the luminosity of the object, or for example, how the collision of the black hole is contributing to the accretion of the system?
Oh, well, this is a very interesting question. However, I consider this a more elaborate situation. Well, what is happening in the collision, you see that material is being extracted. So not here. The material is extracted from the disk, and well, probably we would expect a variation in the accretion. In this case, the accretion would be lowered. On the other hand, this outflow also finally, I don't know what would be the final physics of the outflow. If the outflow reached the jet, or if this outflow falls again onto the black hole. So I think that this would produce variations in the accretion that could be reflected also in the jet, or in the variability that actually is indeed observed from this source that probably Pankaj can tell you more about. This is highly variable in general.
So it's possible that the impact triggered the jet?
Well, the impact trigger outflow. The impact I think could produce variations or variability in the velocity of the ejection of the jet. Because it's associated with the variations in the accretion. If the accretion is you vary the accretion. Therefore, since the accretion is powering or triggering the jet, this is what we understand. Therefore, the jet would be also, let's say, it would be affected by this, but not directly that the impact is triggering a jet. The impact triggers outflow, but not very fast as the jet.
Okay, so can I ask something more? What is the difference between the black hole, the most nearest distance between the black hole and between the two black holes?
Okay, this is a very good question. I don't remember. It would be something around 0.0 10 to the power of minus 2 parsecs, something like that. Of the order of 10 to the power of minus 3 parsecs. And actually, this is a very interesting question because at that distance, according to the masses of these black holes, they are radiating gravitational waves, not detected yet because, well, we don't have the instruments to detect these kind of gravitational waves. But, if this binary exists, they are in the regime of gravitational wave emission for orbital decay. That's in other words, that with these masses and with these distances, the system is losing energy through gravitational wave emission, but not detected yet.
Okay. So thank you again, Juan, for the nice presentation.
Thank you.
And I would like to thank everyone who is following the seminar and participating and contributing with the questions here in Google Meet, and also people following with YouTube. It's always important for us to enhance your scientific curiosity, even if we are from other fields.
The only people outside the group who make up a question was Katarina. Otherwise, this could be considered like a group meeting.
Oh, the team is very interesting for specialists, and also I think it's very important for people also who are not in the field to enhance the scientific curiosity and to train this. And we appreciated a lot your work, Juan. And also thanks, Pankaj, the participating. I think it must be very late in India now.
What the time over there, Pankaj?
We're very grateful also for your contribution. So let's finish now, and hope to see everyone next week for the next seminar. Is invasion percolation solves the Fermi paradox, but challenges SETI programs. So let's finish here. Thank you, Juan. Thank you, everyone.
Thank you, everyone.
Bye-bye.
Bye con Dios.
Thank you.